So the first one, let me back out here. I gotta make sure we can actually read it. Okay, the first one is asking about the anterior cingulate cortex. It's been implicated as possible brain structure that's involved in many cases of depression. Where is the structure? What evidence is described that provides evidence it's involved? So this one with the Lauren.
I have that the anterior cingulate cortex is located in the frontal part of the corpus callosum, and it's considered the node of an extensive network, including the frontal cortex, hippocampus, amygdala, hypothalamus, and brainstem. For the part regarding the evidence, I said it may be involved in depression because it increases the activity in the area of recall, of autobiographical recall of the sad event, and it has decreased activity following a successful medical treatment.
Maybe put anything different or additional or other things they want to add? Like what kind of medical treatments did you?
Just like medical treatments
for depression, yeah. So that could be pharmaceutical. I think there was some stuff on deep brain stimulation too, if I remember right. But that kind of comes up later, so I might not add this now if nobody else added it. But all right, we'll come back to that issue about deep brain stimulation. But yeah, so like this seems to be an area that is, I think the indications are that it is more active in patients with depression. And then they see a decrease in activity in this brain region following effective treatment of depression. So there's at least some, that's almost more correlational evidence that it might be involved. So, you know, they're not directly necessarily manipulating, but it seems its activity seems to be associated with depression. So if you can inhibit this area, sometimes you see lower depression rates. I'll add something about increased activity in depressed patients. Yep. Anything else on this one or questions? Like I said, we'll come back to that issue of deep brain stimulation because I think it's interesting and relevant. But that shows up in a question or two further down. All right, so number 2, I did ask you to take a look at this paper, which is, I don't know, kind of a challenging paper in some ways, although it's the experiment itself isn't all that bad. So the first question is asking what specific gene was tested in this study. So this one went to Olivia.
Yeah, so what I found is that 5-HTT-LPR gene is the serotonin transporter gene.
Then what did you put for, I'll do with this one too before we pause. So what specific result did they find in the study that linked it to HPA axis?
So what I had is people with depression were found to have higher levels of cortisol after stressful events than those without. So since that 5-HTT-LPR gene is the serotonin transporter gene, it affects the HPA axis and stimulates corticosteroid secretion, therefore they're linked to non-effect on depression.
Okay. People with, I'm going to even put certain variants. So I think the idea, so if they, I think what they found here is that those individuals that, because they found like there's certain variations that people have in this particular gene. And so if they had some of these variants, they tended to be prone to be releasing more cortisol when they encountered a stressful sort of a experience. Even though this is a gene that's not cortisol directly related, it's a serotonin related gene. Did anybody see anything about a promoter region? Like that, the PR I think is promoter. I'm just going to add this. So it's a serotonin transporter. I think it is actually a promoter region, right? Polymorphic region, all right. I think it is a promoter, but it doesn't, I've blanked that it's not standing for that. So this is it's a polymorphic region, which means it does vary in the human population. That's what the polymorphic bit means. And I think specifically this is looking at a promoter for this gene. It kind of doesn't matter. The point is that if you have some variants, though, they found clinically that people would have stronger cortisol responses to a stressful event than if people had other variants. And therefore, even though it's a serotonin-related gene, it may influence something about your stress response, and therefore it could potentially be involved and influence something about your response or susceptibility to depression. This was the argument. As far as how that happens, this is why I actually asked you to read the thing. This is going to 2C. So what are the paragraph of discussion cites 3 mechanistic connections between serotonin and HPA axis, and it says, what are they? So I'm hoping we can do this kind of like in concise version, but what'd you get, Laura?
Researchers demonstrated that in animals, serotonin activates the HPA axis by stimulating CRF release, triggering ACTH release, and enhancing corticosteroid secretion.
Okay. Did you get any others? Okay. Did anybody else get any others? That is definitely one. I misspelled something, but. You were definitely in the right paragraph. Yeah?
It also enhances the negative feedback of cortisol.
So yeah, so serotonin may trigger HPA axis, but it also somehow may be involved in negative feedback of the HPA axis, which seems almost not counterintuitive. That's wrong. Those effects seem contrary to one another. There's a better phrase but I'm not working for it. Right? So one is sort of stimulating more cort. The other is enhancing the negative feedback control, so therefore enhancing the ability to regulate and reduce how much cort you're producing. And we actually, I'm just going to remind you of this, we actually talked about this somewhere. Yeah, okay, so here we were talking, I think this is in our section on depression. No, this is in fear, but it's related. So we were talking about HPA axis here. And we talked about negative feedback, where cortisol can feed back through the hippocampus and then negatively impact additional CRH and ACTH and therefore cort production. And we said on the next slide, nope, 2 slides after that, so one of the treatments for anxiety as well as depression were these serotonin-specific or selective reuptake inhibitors, SSRIs. And so what these things are doing are affecting your serotonin load. They're increasing your serotonin load because they're inhibiting this transporter. And we said one of the things that may be happening is that they may increase glucocorticoid receptors in the hippocampus. So if we increase glucocorticoid receptors in the hippocampus, I'm going back, that may facilitate this negative feedback loop. So we actually did talk about this in that effect in lecture.
I'm just trying to make sure I
Yep.
have this right. So enhancing the negative feedback loop enhances your ability to regulate. Okay.
Yeah, so if really what it should do is it should help us to prevent situations where we have a runaway cortisol effect. So the point of this is that, so this is a cortisol-based system here, but what serotonin is doing is it's facilitating this part right here, where cortisol is being received by the hippocampus through glucocorticoid receptors and therefore causing the negative feedback inhibition. So while what we've said already in this question then, we said part 1 here that serotonin may actually activate the HPA axis, so that would result in more cort. But then here this is showing, and this is exactly what we were just talking about, that this enhances the negative feedback of cort on the HPA axis. So serotonin isn't directly doing that. It isn't directly inhibiting the HPA axis, but it's facilitating cortisol's ability to help regulate itself. Am I put anything other things? I have a cheat sheet here. So there's a whole paragraph here. One Yeah, I'll just do this one. So it says mice with the serotonin receptor knocked out with a serotonin receptor knockout. So this is where you're genetically manipulating these mice such that they no longer have a serotonin receptor. So this was, again, in an animal study. They found that if you knock out their serotonin receptor, they then have an increased stress response to some sort of an acute stressful event. So they'll have a larger cortisol response, which is, this is an animal study, but it's very nicely tied then to the study that was found here, as far as, this was in human patients. So, the human patients, they weren't knocking out people's serotonin receptors, but they have a regulator or something, a gene that's involved in regulation of serotonin levels, a transport protein that regulates serotonin levels. And if you have a certain variance of it, you are more likely to have increased cortisol responses to stress. And they have a similar kind of effect down here in mice, where if you just flat out knock out a serotonin receptor, then you can also get the same kind of an effect. So there seems to be some sort of a mechanistic relationship here, this is the whole point of all this, between the HPA axis and serotonin, even though, in a way, they're kind of two separate systems. Serotonin clearly impacts HPA axis somehow. And that's why SSRI drugs can be helpful in cases of treatment of anxiety or depression, especially in terms of its interplay with the HPA axis. Okay. That's the hardest part of this question, I think. So it's last bit is if individuals with disrupted serotonin function have a more reactive HPA axis, and that is what we just got done arguing, what role might a hyperreactive HPA axis play in triggering depression? So this is trying to close the loop here. So this one went to Sarah. What did you get? I missed the last little bit, but I think this is the gist. Yeah, so if you have a hyperreactive HPA axis that may increase your depression beyond what you can control, and that's because this is your main stress response. So basically, you have a hyperreactive stress response, and so any kind of stressful situations you encounter, you're having a more severe reaction to those stressful events. And that, in turn, could lead to depression. I think this could also explain why this could lead to anxiety, because you've got a larger stress response. And the stress response maybe isn't directly causing the depression and directly causing anxiety, but it's feeding into the systems that must be involved in control, or the systems that are involved in regulation of mood, and systems that are involved in regulation of anxiety and fear responses and that kind of thing. So a hyperreactive HPA axis, as can happen when you've got disrupted serotonin function, can, I would say, sort of predispose you to these kinds of mental disorders. Does that all make sense, more or less? Like the big point of this question on the homework is really to try to link then what we were learning about HPA axis to the fact that a lot of the treatments for depression are focused on serotonin, which doesn't seem like it's tightly linked. So there was some discussion of this in the lecture, but then this is a paper that's trying to pull all that together for us a little bit. All right. I'm seeing no hands, so I'm going to keep going. All right, so next up, I think this one I pulled out of the book, but I thought it was kind of an interesting question. So depression is often accompanied by bulimia nervosa, or maybe it's the other way around, where bulimia nervosa is often accompanied by depression. Bulimia is characterized by frequent eating binges followed by purging. And so the question is, where does the regulation of mood and appetite converge in the brain, and does this suggest some sort of mechanistic link between the depression and eating disorders? This is a speculation question. I'm asking you to speculate as opposed to, find some specific reference for this. But there's at least maybe something there. Chelsea, you got this one. What'd you get?
So I thought the structure of the brain that converges the regulation of mood and appetite is the limbic system, because the role of the limbic system controls basic emotions as well as instincts, which includes hunger. So this could definitely suggest the link between depression and eating disorders.
Wow, huger. Anybody put anything different or additional? Everybody key in on a limbic system, or did you key on something else? Yeah.
I don't know if this is part of the limbic system, but I wrote the hypothalamic pituitary adrenal axis, which is like responsible for regulation of mood and appetite.
I don't know what role it would have in appetite per se, but I mean, so definitely stress responses, which can influence mood. Did anybody see specifically where appetite is regulated? It's what I thought you were about to say, but it's close here. Yeah, so it's hypothalamus. And we may have mentioned that like way back in chapter 7, maybe. I don't remember if it was there or not. But this is the main appetite regulation center. So we just got done talking about this a couple weeks ago in my anatomy and physiology class. So appetite's regulated in the hypothalamus. The hypothalamus is part of the limbic system. So, and then the hypothalamus is also involved in this HPA axis. It's involved in other kinds of emotional regulation. Mammillary body, for example, is involved in the limbic system, and that's part of the hypothalamus. So I would agree on limbic system. I would even, probably point my finger at hypothalamus. Now, I'm not claiming that it's definitely like that's the thing that connects bulimia to depression, but that one structure is certainly involved in both kinds of responses. So we talked about depression, HPA axis, involvement in depression. The H in the HPA axis is the hypothalamus. And then the hypothalamus is certainly also involved in hunger regulation.
Do you know where the body dysmorphia might come from? Which area of the brain that would be?
What was the word you just said?
The body dysmorphia, where you see yourself.
Oh, I don't know. Yeah, I don't know. That's getting into kind of getting into cognition stuff. So, I mean, I would propose, this is a wild speculation, but this sort of your poor body image, that perception, I would guess is something about interpretation of your sensory areas that may actually be happening more in frontal cortex. So I would argue that's probably frontal cortex as opposed to hypothalamus. But that is pure speculation, just based on, that seems like advanced brain processing function cognition stuff. So I'm going to say frontal lobe, anterior frontal lobe. All right, so again, I'm not trying to claim that that's exactly where it is, but in a way, the question is there to help us remember what the hypothalamus is doing and the fact the hypothalamus is involved in several of these systems. Definitely, we talked about HPA axis. Hypothalamus is also our appetite regulation center. It does lots of stuff. Okay, number 4, there are non-pharmaceutical approaches to treating affective disorders. So we're supposed to try to identify what's going on with each of these. So electroconvulsive therapy. This is a fun one. I first heard about this in, there was a movie called Return to Oz that I used to watch when I was a kid. I don't know why. I just liked it. But they were trying to give electroconvulsive therapy to Dorothy to make her forget about Oz. It was pretty bad, but there was this crazy puppet thing going on, and he was allergic to eggs. That's how they killed him. Okay, so Josh, you got the...
So electrical currents are passed between electrodes placed on the scalp. Localized electrical stimulation triggers seizure discharges in the brain, but the patient is given anesthesia and muscle relaxants to prevent violent movements. And then I said relief can come as quickly as one session. And if the person has depression or mania, they target the hippocampus. Side effects is that it can cause memory loss.
Yeah, oops. Yeah, so I don't know if you guys, we never got a chance to talk about memory. There's a story of this guy, HM, who they removed his hippocampus because he was having seizures. And it worked. It stopped his seizures for the most part, but they kind of induced an anterograde amnesia, so he couldn't remember anything from age 27 on. Because hippocampus is so critically involved in memory formation, but it's certainly directly involved in limbic system. And I think that makes sense, and it's intuitive in some ways, because a lot of the things that we remember the best are also emotionally charged. And so limbic system definitely has an interplay with our memory systems. But it is the case that you can severely, that you may be able to help effectively kind of reset neurotransmitter loads or something by basically hyperstimulating these neurons, kind of getting them into a different state through this sort of induced seizure thing. And then that seems sometimes to help with the person and has a dramatic benefit. And now, at least, they give anesthesia and stuff so you don't feel it. I don't know that they would have some years ago. That's the argument, though. So again, you're trying to impact something about the limbic system, and it's kind of almost seems like a barbaric effect, but but it's kind of a brute force method, I guess is what I'm trying to say. But it does seem to work for some people. Psychotherapy. This one went to Danielle. What'd you get?
I said talk therapy that's used to help patients overcome negative views of themselves and their futures. And then it's thought to have an effect on the cognitive neocortical control of the activity patterns.
He said cognitive neocortical control of.
Activity patterns in destructive systems.
Yeah. People have been doing talk therapy and for a long time. Cognitive behavioral therapy has been is very well supported with good evidence behind its efficacy. I think one of the really cool things that's happened in recent years is demonstration that you can see changes in brain activity, cortical activity, even to some degree maybe neurotransmitter activity, as the result of cognitive behavioral therapy. And like that's really cool. We read a paper in, I don't even remember what the focus was, in neuroscience seminar this semester. Was it depression? Does everybody remember that's in seminar? Where they found changes in methylation patterns as a result of cognitive behavioral therapy, which is just freaking mind-blowing. I mean, just really cool. Was that your paper, Danielle? Was that depression, or was that anxiety, or I forget what they were.
It was like looking at like depression. But
Yeah.
you look at like
It was like anxiety.
Yeah.
And
Yeah. But my God, talk therapy, and they're getting like molecular level changes. I'm like, oh, so good. That's just like, then they replicated and they didn't get an effect and all. But, but still, it was really cool. One of the 2 times it worked. It was really neat. Okay, last one was deep brain stimulation. I think we have time for this. What'd you get, Sarah?
it involves implanting electrodes within certain areas of the brain to produce electrical impulses that can regulate abnormal impulses or affect certain cells and chemicals within the brain.
Yeah, and one thing, this is linking back to our first question, which was on angular cingulate cortex, and not angular, anterior cingulate cortex. I'll just write this down. So it's almost a little bit counterintuitive. But one thing that this deep brain stimulation will often do is it will upregulate it'll upregulate inhibition. So, inhibition is an active process. So that's the thing you have to sort of keep in mind. So if you increase inhibition, through this deep brain stimulation, that can then dampen the activity and reduce activity in certain brain regions. And so one of the things they talked about in one of those boxes for question 1 is that if you do deep brain stimulation in the anterior cingulate cortex, you can actually decrease the activity of the structure and sometimes help people with depression. We are kind of out of time, but I don't want to stop. Can I just say this one? I'm sorry, Monica. But so just in the light of, because this is the last question, I don't want us to have to meet for no reason. So the deal with this one is that a lot of the neuroleptic drugs are dopamine receptor inhibitors, right? So if you block dopamine, that is going to have a similar effect to a situation where you're not producing enough dopamine. And that's what happens in Parkinson's, is that you don't have enough dopamine, and therefore you can't initiate some of the motor actions. And so the result is that you're basically inducing Parkinson's sometimes with the side effects of some of these neuroleptic drugs, where you get people that have resting tremor and difficulty initiating motion, which is why sometimes people have a hard time staying on those drugs because they're so frustrating with the side effects. So this is the idea, is that it's a dopamine receptor inhibitor. Here's the deal. We're done. I still will be here, but I wanted to finish since we were 30 seconds away from finishing. So we are done. But if you'd like to come for sort of like a first review session on Wednesday, I will be here and happy to take questions. If nobody shows, or even if everybody shows, we'll still do the review session on Friday as well. But aside from that, that kind of is a wrap for the semester. So thank you guys. I hope you enjoyed the course. And I always enjoy this course. I appreciate your efforts this semester. If I don't see you at either of those times, then I will see you guys a week from today for the exam.